So this is actually some sort of material that we're discussing, and in particular, then we're going to see, for example, how we could exploit, and here is previously suggested, because in the original slides that I was saying, that I was providing, the order was shuffled, but I think it's more important that we start from use case scenarios, so you have a clearer understanding how to apply AI, rather than the other way around. So one way is actually whatever you're referring in video games as goal-oriented action planning, but that is actually an extreme simplification of actual reference literature. So if you're going to do eventually research on this kind of stuff, in literature is actually referred to goal-oriented action planning. So automated planning, because it actually comes from the field of robotics. So the thing that you have in common is that you have a goal that you want to pursue, and then you want to traverse the possible states of the possible configurations through actions. Actions will change the state of the environment, and that could be traversed as a graph. So I think that with Rich, you would see, like, after seeing like a star algorithm, then you'd see like a simplistic way to traverse the graph from actions. But in the actual use case scenarios, when you have actions involving outcomes and where everything cannot be hard-coded, then you're not actually creating the graph, because it could be like explosive, as we're going to see later on with the module. So you're doing a visit at runtime, and actually you're not only traversing forward, but you're trying also to do the other way around. So from the goal, you're trying to reach the current state. But these kind of algorithms are quite convoluted, so we're not going to dwell into much details. But really the idea comes from what is actually the scenario and how that could be applied. So I wanted to just, like a thought experiment, provide the Sims 4 as a use case scenario. Because even in there, you have like some goals that you want to pursue, and that is actually personal as you as the player, but you have like internal configurations that are low or high and are dynamically changing. So for example, you are a kid, and so you might assume that all the key character values are low, and you want to increase some of these. So one way is to enact some of the actions that the game provides you, so to increase, for example, responsibility. And in here you have actually a good mixture of everything, like internal state representation and positive feedback. So as you could see in here, how am I saying to a player without reading the manual that the action that they are providing is positive? So I have multiple ways. One way in here is actually using the color green. So usually in the Western culture, that is actually associated to something good, like the green semaphore, so something that is good to go. And I have a plus, so I know that I'm increasing with something, and the little animal in there is actually providing the information that is actually something new which is achieved. So you have everything providing positive feedback to the player that has actually done something positive, and then definitely you need also to provide some kind of textual information, responsibility, and contextually I'm also providing the image in the context of all the character values, what was increased, so I also have a green arrow in there. But I also have the possibility of increasing the other parts, so the other parts that are in red are actually providing like negative feedback. So I know that given that it's very young, the character has a very low conflict resolution, so that might provide a prompt to the player to increase that. And how to achieve that is actually through action. So in here you have, like on the right-hand side, a representation of what is actually an internal state, and an image providing you the information that by performing the actions I could change my internal state or even the state of the world if I'm interacting not within myself but within the other players within the game. And so you might think that you also have like values associated with that, whether that is low or high, and then I know that if I traverse a given path, which is actually associated to a specific action, then I want to maximize one of the internal states that I have. So that actually provides just a general understanding of the correlation between actions, internal state, and increase of value that is going to be happen in here. And actually in here is, everything is described in here. So why is that relevant? Because then we're going to see also rewards. Like in here, the green part might be seen as a reward. That is going to be also relevant in the context of Markov decision processes, which are actually the key element of reinforcement learning. And so you know that you have the rewards that will have like, that could also be like in this scenario, multi-objective functions, because I want to maximize not only one objective like responsibility, but multiple things. And then if I want, I could also provide like a ranking score, which is actually the thing that I want to privilege, increasing one before the other. So that is actually what is multi-objective functions. And then you have also other algorithms, but to have like multi-objective optimizations, but we're going only to see single objective optimization in here due to practicality. Then you could assume that you want to do something like multi-objective optimization. You could always create one function taking all the arguments as an input and then providing one single score as an output. That is actually the rough understanding. And in here, you might have, for example, the internal states, the desirability of a state might be hard-coded or might be something inferred depending on the reward that I'm having. And we're going to see actually the both use case scenarios within these lectures. But, so in order to provide something more dynamic, we need also to discuss a bit more about strategic games. Because actually in the other one might seem boring because you don't have like a strategy that you need to enact, but you have like the god that is actually deciding something. So either you have a plan about something or the game is not going to tell you anything at all. So you need actually just to fulfill your plan and traverse whatever depending on the objective that you have in mind. In here, the goal is actually more immediate to understand because otherwise you would be killed in this kind of game. So the goal is actually to kill the others and not to get killed. So also by changing the type of the game, then it might be more easier to grasp what is actually the intentions. And definitely, then I know immediately what is actually going to be the action. So if I do not want to be killed, I need to shield myself, to protect, and in order, for example, to win the game, potentially kill the other opponent. So that automatically provides you in mind which are the actions that are required to fulfill the goal. So even in that, simplistically enough, everything could be represented as a set of clauses, like I have an effect that is actually causing like a consequence. And so if the preconditions are met, then something is going to happen. And it's going to change not only my internal state, but the external state. And so you might, even in this scenario, might have multiple goals, which are not self-values of the character, but actually patrolling or killing the enemy. So in this case, the internal state of what I'm doing and that what might come. So usually if you're using like state machines, you could code like two states, and in each state you are associating, so for example, some actions. In here, you're not creating the graph at all. You're just creating like a set of rules, and that from the intuitive point of view is going to generate the graph for you, given this kind of set of rules. And we're going to see a scenario actually within the slides. And the problem is that in this scenario, it's not like when you are coding, so that's why it's impractical to create like a state machine. So you need to create 120 actions that might provide an outcome towards one of the characters, and then they will change the value dynamically. So it's actually very convoluted to define that. And so you have actually an explosion of states. So it's actually better not to use training, because that is also what you're doing in robotics. So you cannot usually train a robot because, for example, if you're sending something to Mars, then you need to code all the actions. So that is how the rovers on Mars were going. And so you need to say, okay, if that happens, then you need to do something like that. So you're creating a plan that the agent is going to pursue. And definitely, you have something more complicated that we're not discussing here, which are actually the increase or the decrease of the value. So in the field of automated planning, those are called fluents. So you have like numerical variables which are not necessarily associated to a state, but are changing with the actions that you are performing. And then you could reach the same state with different actions, and so you could reach the same state with different variable values. And that are actually helping. But we're not going to see these algorithms. And so within the slides, we're going to also to contextualize this in two only use case scenarios. One, which is actually platform generation, and the other one, which is actually related checking whether a game is solvable or not. And so in there, we're going to use this kind of actions with the context of the lectures to associate, for example, in a game of keys and doors, then I achieve a key. With that, if I could reach the door, I could unlock the door, and that grants me the access to other doors or other keys. So you could structure actually the set of actions required to finalize a game in a logical way, and with that, you could instruct an agent to potentially do an action, or from the other perspective, you could provide hints to the agent, so to provide suggestions if it is actually not progressing in the game after a given time. And that actually leads to the next slide, which is actually procedural generation. Before I continue, are there any questions, by the way, related to the things that I was discussing now? Okay, so the other thing is that usually, even in the context of dissertations that have been done so far, usually when you have in mind to create like a platform, is not related really to a specific kind of context or to a player or just generating something. And maybe also for a dissertation point of view, that is actually also very convoluted to generate something and avoid a lot of bugs. But in real games, you are also doing something more than that, which is you need also, most of the times, to change the difficulty, so change the platform, depending on the level of expertise of a specific player. So why that might be the case? Maybe if you are providing a lot of choices to the player, to a beginner, then he's actually lost in navigating the map and doesn't have like the focus to know immediately what to do. So one of the ways is to provide, for example, you know, because you are generating the map, even though it is hard-coded, or even if you are procedurally generating that, but that if you need to, for example, kill a specific kind of enemy, you would need some kind of armor or a specific kind of weapon, and therefore only users that have actually XP level above a given threshold will be able to beat the monster. And then definitely I could also assume that I cannot achieve more than a given number of battles, so I have like a maximum number of expertise that you could achieve. So all these scenarios might be used when generating the map to prune the path that might be actually very difficult for a beginner to pursue, or, for example, to not provide all the information and just provide like a narrow map that is actually easy to navigate. So if I know which is actually the expertise level, I could also dynamically change the map. And you could do that because you might associate this kind of values to the objects that you are while generating the map, or even if you are encoding that. And then depending on that is like increasing the XP, then I might unlock something more. So for example, then the other thing that we're going also to consider is that I want to have also like a shorter game, and that if the game is actually prolonged, then if I am achieving another threshold, then I could also add secret rooms once the player is actually more acquainted to the map. So it might be also know all the parts and might be able, okay, this is actually something that I have not seen before, and so I want to unlock this part. And the other important part on procedural generation is that, yeah, it's very easy if you are just hard coding some levels. It's even easier if you're doing like other video games that you might find on Steam, where, as it also happened some years ago, a developer say, okay, if this game is actually very difficult to pursue, to do, I will tell how to progress with the game, and it was actually only telling how to progress on level 2, 3, and 4, and not all the details for level 1. I would say, but believe me, there are level 2 or 3 and 4. And actually then, a Unity programmer actually saw that level 2, 3, 4 on the files were actually just the splash screen at the very beginning, but there was only level 1, and actually the game was unsolvable. So, beside all this kind of trickery people that are trying to trick you, usually if you want to design a lot of levels, you need to create like a very compact world. And the challenge is, what if I want to explore like an entire universe? Then the problem is that if you're trying to do that, that could not fit inside your machine, because you have like an explosive amount of memory that is going to be required. So under the assumption that you have like 10 to a power of 19 planets, and if you want to navigate this map, it's going to be unfeasible, because you would need to store like a graph taking at least 10 to a power of 29 gigabytes of memory. So it's infeasible for your company for storing that large graph in a server. And what if one of the nodes goes down, then one part of the world is actually not available and such. So doing this kind of task is impractical. So what they were doing in No Man's Sky in order to avoid this kind of problem? So that is actually everything available on the web, so it's not like industrial secrets that I'm revealing you. So everything is actually online. So in order to generate the planet, they were using mathematical functions. So they were ensuring like some sort of determinism. So I know that if I have some random seeds that are initialized, and that provides the parameter of my generation of the algorithm, then I'm actually generating the world with the caves, with the ground, with the hills, with the mountains, and everything of the sort. So if you don't know what fractal is, then you have, for example, Mandelbrot sets. So those are fractals. And the interesting part about this is actually that you have like a repeated structure. So if you're also seeing some kind of vegetables, like this, have also a fractal structure. You see, you have the whole vegetable, which is actually replaced, and you have that the smaller structure is actually reflecting the larger structure, and that is also associated with ferns. So also ferns, as you see, they have a fractal structure. If you're taking one specific part, the fern, then is actually reproducing the overall bigger size of the fern. So fractals are very common in nature, and that's why the game designers are using that, because that, if well tuned, could also provide something like realistic generation. And then you have something more difficult, which is you want to create other features like animals that are interacting in a given way, and you want to also create emergent behavior in characters. And then you want also to create like night and day cycles and the perception of the game physics. So everything cannot be hard-coded in there. So you need to actually generate some rules, have some seed values, and depending on that, you're ensuring that the world that you're generating is always going to be the same. So whenever you're exploring the planet, what would happen is actually your machine will not remember the overall world, but will only have the seeds and the generation function, and then it's guaranteed all the time to always generate the same planet. So that is actually how it's going to work. And in addition to that, how then you're ensuring that if a friend visits your planet, they're going to share the same experience, then they know that, and so when you're going online, then the computers are going to share the seeds. So whenever your friend is going to come to your planet, then they're going to have the same experience that you shared. So all these kind of trickeries are actually ensuring that everyone has somehow the same experience of the game. And then we're connecting back to reinforcement learning, given that we were talking about like insistent values, but they're also used like in goal-oriented planning and a set of actions. So then you have another thing, why also modeling actions is relevant. So if you're using like a simplistic approach like AI, for you could also use whatever approach simplistically enough, but just to provide some insight on why that is actually troublesome. So let's suppose that you want to like use Dota 2 or something of the like. Then if you want to create just, for example, an AI for Dota 2, then the thing that is actually going to happen is that you need to train the AI for a huge amount of time after, in order to have like a realistic behavior without any kind of notion of actions. And the other thing is actually, that is also very relevant to consider actions even in strategic games, because depending on the actions that the player is performing, you could predict what is going to be the next move, like a chess player. So if you are playing chess or checkers or anything of the sort, then you know that if a player is moving, then he has in mind probably a given specific move. Then you are planning as a human ahead like 2 or 3 actions, or the best player even 6 actions ahead. And so they're actually mapping the environment, and so they know what are going to be like the potential action that he's trying to do, and they're trying to counteract as much as possible. So doing that is actually relevant specifically if you're going to work in turn-based game strategic. But it's going to be very problematic, and you see that all this kind of sort of games take a lot of time for loading the model and to set up. And the other thing that tells you that they are actually using this kind of behavior is actually when you're using the game. So for example, if you're using like this mod to Civilization 4, then you'd see that after playing the game in a given way, they will adapt to your style of playing. And so if you're able to conquer a village or any kind of city in a given specific way, then next time it will be harder for you to do this, because actually they are studying your tactic and then trying to enact countermeasures. So, and then you would see that if you are lost interest in the game, and then you are giving up because you're always defeated and something of the like, after a long time, then you will never log into the game again, then it will become, again, easier to play. So that entails that you have some kind of AI, which is actually adapting to the user experience of the player, which is also then relevant. And the other thing is you have some kind of AI, which is also trained while you're playing the game, potentially. So that provides like use case scenarios for that. But we are not required to do this in the lecture. Nevertheless, we're going to see like dynamic AIs that are just exploring the set of possibilities at runtime. And we're going to explore something like an intuition of train-based. But we're not going to use like complicated machinery too much, because that is actually out of the scope. So my aim is to you to understand the underlying mechanics. Even for reinforcement learning, we're not going to use like deep reinforcement learning with neural networks, because even if you're using a neural network, all they're doing is associating a state to an action and or a current. Actually, they're associating the environment that you are perceiving, and they know which is actually the current state that you're at. And given that, they are predicting which is actually the best actions that you need to perform. So everything that a neural network does is training a transition function. And in here, we're not going to exploit too much neural networks, but we're going to see what is actually the mechanics underlying that. So the neural network is just approximating the graph with a set of actions and preferred actions and weights. So we're going to see that perspective. So it will be even clearer for you, which is going to be the mechanic. But reinforcement learning could also definitely go beyond that. So that is also available online. If you're taking like Ubisoft was actually using reinforcement learning to learn to drive a car, which might be daunting, but if you think about it, it's actually quite simplistic, because, and then they did something different, but just to make a car move, you just need to say, like, I want to brake or not brake. That might be like a binary in one setting, action, brake or not brake, accelerating or not acceleration, and steering left or right. But that might be not realistic enough. So the other thing that you could do is actually provide a gradient between 0 and 1 on how much I'm braking, how much I'm accelerating, and how much I'm steering left and right. And then the target is actually to reach the goal, and the way the car is actually following the path is quite straightforward, you see. You could also have, so if you're just training something without perceiving the environment, then it will never learn anything at all. Then you need to assume that you are seeing the road, and which is actually the path. Then you need to provide constraints like, for example, if I want to, like the barrier, then I'm losing reward points, and then if I'm going towards the end, then I'm having like a positive feedback. So that is actually the usual way to train this. But the most important part is actually another paper that was also published in Nature, which is actually related to how to train AI for car driving and also beating other human players. So the thing that they were doing is actually training an AI to compete against a human player, which was actually simulated in a video game as an environment, and then it was trained actually to do the same, but with an addition that you were maximizing the reward if you reached the end of a track and you were actually first. So whenever you cannot foresee all the possible interactions and you will just give up and you have a lot of money and you have a lot of time to spend, then you could just use reinforcement learning to do something instead of hard coding something. But you have actually two benefits of this. This actually provides you like a no-brainer way to train something. You know that the machine, like a Harry Potter wizard, is going to pop up with intelligent behavior if you are, by the way, setting up the training efficiently. So if you're providing reward functions that are not correlated to the goal, the AI is not going to work at all. So only if your reward function is related to the notion of the goal, then the AI is going to learn to meet the goal. Otherwise, it's not going to learn if you're not providing like the exact reward function. And that's why at the very beginning we are talking about graphs and states and goal state, because otherwise it will be actually troublesome to understand how to correlate reward functions to actually the achievement of the goal. But nevertheless, then you have also benefits for automated planning, which is, for example, in critical scenarios, you cannot store an entire model in primary memory and you need something more compact and efficient, and navigating the state space is actually better if you're using specific heuristics that we're not going to discuss. So similar scenarios then do not only apply to cars, but also in a city scenario. So even in there, I want to reach a specific kind of destination, and then I want to train my AI to reach that. And then my character could do some actions like forward and backward. In here is just joystick movement. So in here is just yes or no, not a gradient between values. Rotate, jump, and double jump. And that might be required to like do parkour over the buildings or something, but nevertheless to crawl the city and then eventually reach the target point. So even in this scenario, if I do not want to say the agent how to reach the goal, but just figure out that yourself, then one way is actually to use reinforcement learning. And by doing that, then even in this scenario, if you're providing like the exact reward function, so whether the agent is allowed to perform an action given a given environment that you're sensing, then it's going to be good. So usually there's always the correlation between environment that the agent is sensing, then that might change dynamically the reward function, which is not necessarily fixed. And then depending on that, then I would know which is actually the best action to perform. So the other thing is actually the agent needs to figure out the correlation between the action that needs to be performed and the environment which is sensing. So if all the time I'm always perceiving the same stuff, then I will have no correlations and no preference of performing one action against the other. So the way the agents should perceive, it should be perceiving the differences that are then guiding to providing the action so that the reward function could be learned, so that could be correlated to the actions to be performed. even in this scenario. And then that's pretty much it. And the idea is going to be that this kind of topics are going also to be correlated somehow to the coursework that you're going to do. So in here, I'm just providing like realistic use case scenarios. But I'm aware that also in the coursework, we need to like say, provide like a low tire information. So the other thing that I will provide also as a caveat is that most of the techniques that I'm going to provide are going to be what is called turn-based. But that does not stop you for applying that also the same techniques in real-time scenarios. Just to provide an example, let's suppose that you are in a battle like Tekken 3 or something, and I'm very old, so I know Street Fighter and Tekken 3. So the thing that you're doing whenever you're battling is actually performing an action against the other agent, which will counteract with another action. So you see, even though you have time, which is actually flowing, everything could be discretized. So whenever a player is doing something that you're chunking up, I have one event under the assumption that then the other player is actually doing nothing at all. But you could also have like a timestamp when both opponents are doing something at the same time, like synchronously. Then you could also have like one shot of the game, snapshot of the game, where both agents are doing something. Then how could you model, for example, a combo where multiple actions are performed, like the other agent will always stop and this agent is actually providing multiple actions at the same time. So intuitively, even though I'm providing the understanding for discrete environments, then everything could be turned from real time into discretized, because that is actually what happens even if you're using reinforcement learning in Unity. So at each delta update is going to consider that as a frame when the environment is perceived and for which you have an action which is actually associated to the perception of the environment. So similarly, if you're having like, if you're doing no actions, then you could assume that no event is happening. As soon as an agent is performing an action which is relevant for the focus of a play, then you'd know that something is happening. So, and you should have also in the code base some examples that I was providing how a real-time battle between two agents might be actually exploit either min-max algorithms or even reinforcement learning using like Markov decision processes. So that is actually the other caveat that I wanted to provide like a clarification. So besides this, are there any questions related to anything that I explained today or the connections between this stuff and your coursework? So my suggestion would be, given that by now I know that someone is already trying to design a game, someone is still working on the tutorials and stuff, to think about a game that you want to design. And it could be also like car racing, and then you could exploit something like to train the agent. Or you could also have like a first-person character or anything of the like. But the idea is, as soon as you have an idea of the game, please try to think about how the key concepts that are provided in here might be exploited. And then, how could I apply this technique in my game? Then I will be there in the practical session, so if you have any kind of puzzlement, then please ask me or any kind of attendees of a practical session, so to provide more guidance. So the key to success, as I'm always saying, is asking. If you're asking, we say in Italy, you're going to Rome. If you don't know the way and you're asking, then you will find the path. Otherwise, if you're not asking and not interacting, yeah, it's actually good that you're trying to sometimes to figure out by yourself how to do something, but if actually something is daunting, then we're here to help. So So in order to help you have like some kind of materials and some examples that are on Canvas, but I'm not going to provide like Unity examples of games doing that, because that is going to be your purpose of your coursework. I'm just providing code base in C#, and then it will be like your responsibility of applying that in the game. The other thing that I want to also to clarify, you are not required to strictly abide by the use case examples that I'm going to provide in the next slides and the next lectures, because those are just contextualizing something like low-hanging fruit to make a theoretical concept more reachable and understandable. But that might be very far apart from the game that you want to design. So that's why interaction with us is going to be like beneficial. So if you want to double check if you're doing something correctly or how to provide an enhancement to that. Before I say class dismissed, are there really no questions? Do you have questions? Then, if not, then I would just say class dismissed, and I will be here for 5 minutes if you have any kind of queries. Thank you.